What's up? I'm Austin Griffith. I'm here with Chris and Jay, and we're talking about Reach. It's kind of a big jump to go from I'm using Web3 and Solidity and Ethers and Waffle, and now this it's a different paradigm almost, right? You've got a different programming language. The app building stuff is going to be interesting to me. So I just hope that I can kind of dive in and learn how to do this. I'll set up. Who wants to be the screen sharer? Can I set Chris as the screen sharer?
It'll be Jay.
Jay. All right,
Yeah.
setting Jay as the screen sharer. I'm gonna make you the host. There we go. Awesome. So basically, I mean, like, I'm brand new to this. I know that Reach is a different programming language. I've seen maybe into the syntax a little bit where it looked like kind of we had Alice and Bob, and you kind of had the actors within the network, and the actors were sending stuff to each other. Sort of like after we learned what Solidity was about and how to use it, you kind of like re-architected the language around how we're using it. It seems like that's what's going on, but could you guys give us like a good intro to it, and then we can kind of like get in and just kind of like build something. My goal here is, can we build some simple Solidity and then build an app that kind of talks to that Solidity?
Sure. So I'll just start, do a little bit of intro. So my name's Chris. I am the CEO of Reach, and Jay here is he's the CTO. Um, we created Reach because what we did is we saw that there was actually a big problem with blockchain development is that it was very hard. And it's very hard for multiple different reasons. One of the reasons is that it's too low level. You have to really kind of like program every single step of the way. Um, and not only that, but so we also wanted to make sure that we provided a language that looks familiar. So that's why our Reach is a subset of JavaScript. But we also, the other problem that we saw is that blockchain development is really more like you're not really building one application, you're building multiple applications that all speak together and they all have to stay in sync. So we wanted to kind of abstract away from that as well and kind of output the entire dApp rather than just the smart contract. And then, of course, the other issue is that safety. So uh, you see all these news articles about hundreds of millions of dollars lost because of mistakes. So we wanted to actually protect against that as well. And then finally, we wanted to we believed that the future is a multi-chain world. We believe that that different blockchains will have different features that different developers will want. So we want to make sure that the developers can learn one language and decide to choose which blockchain purely based off the features rather than having to learn completely new technology every single time that they want to do something else. So that's really kind of the motivation behind it. And from here, I'll actually pass over to Jay to kind of talk about how exactly we solved all these issues.
So that, just to dive in there, you said
Sure.
when I'm thinking about taking my app to a different chain, I'm thinking, is the chain EVM compatible, right? That's like my big
Right.
question as an EVM developer. What you're saying is let's figure out the model down here and let's make the code fit the model, and let's bring it up and let that same model apply to different chains. What,
Exactly.
like, if we did build something here today, I'm assuming we could deploy it to mainnet Ethereum, but where
Correct.
else could we deploy it?
We can also deploy it to Algorand today.
Okay.
So on Teal. So I mean, I'm not sure how much you've looked into Algorand, but the gas fees on Algorand are pretty much non-existent. I think
Cool.
it's like 1/1000th of an algo is what it costs to actually do a transaction. So if that's gas things is a issue,
And
that's
it's not EVM compatible, just to
not
be
at all.
clear. Cool.
And
Dope.
I
Awesome.
think I
Okay.
think Jay will actually even show you how different it actually is, which is pretty
Okay.
neat.
I'm excited. Take it away, Jay.
Okay, well, so on my screen right here, you'll see on the left-hand side, we have our documentation loaded. So the documentation is at docs.reach.sh. Let me just type that over here real fast. docs.reach.sh.
Got it. Oh yeah.
Okay,
Oh
there
yeah.
you go. Nice and big. And what I thought I would do is we would write a really simple program that kind of follows the tutorial that's on the documentation. So if you wanted to go slower at home, then I would recommend going to the tutorial. So I thought that what I would do is, as we write the program, I'll talk about the kind of the design paradigm of what Reach is like. And one of the main things is that when you write a Solidity program, you basically have to think about there being this object that's out there on the blockchain, and what your main concern is what is the state of that object? And then, given that it has some state, which state transitions are allowed, and in what situations are they allowed? So like the proper way to design a Solidity program is basically to like write a state diagram that describes what goes on, figure out a way to map that state to variables and storage and whatnot, and then design the transitions, and then make sure that all your require statements on each transition arrow, the transition arrow, essentially the methods, actually ensures that you're going from one state to another. That's the correct way to design a Solidity program. The problem with that is that that basically just says what your smart contract is, but what you really want to do is you want to make a distributed computation. When I say a distributed computation, what I mean is that you have in mind some set of actors who are going to interact with one another. And if you didn't have the blockchain, they would interact directly with one another. But of course, interacting directly, they now have to have trust. And essentially what consensus networks do is they allow you to have decentralized parties interact with one another without trust, because they don't have to rely on each other to execute the terms of the program correctly. They can rely on the smart contract enforcing that. So given that that's the ultimate role of blockchains, no one really cares about blockchains. What they actually care about are those distributed computations. So the idea is that what Reach does is that you write the distributed computation on its own, just by itself. So let's write a really simple program. So when you write a Reach program, you are writing a subset of JavaScript. And the main way that you define your program is that you're going to define an identifier named main, just like in C, you write your function named main and so on. And you're going to be making a Reach application, so we're going to call the reach.app function. And this function is going to take 3 arguments. I'm just going to fill in those 3 arguments, and then I'll talk about what they are in a moment. The first one are a configuration that you're going to give the Reach compiler about how you want your program compiled. We're not going to do anything interesting with this, so we're going to skip it. Okay, the next one is a list of all the participants of your program. So we're going to follow like standard protocol description literature and call them Alice and Bob. And that's just a cute name that we use in the security protocol literature to talk about A and B, just sort of arbitrary people.
Do those link to an address, or could that be a contract? I suppose this identity basically is going to be different depending on the blockchain, and you guys kind of handle that underneath the abstraction.
Yeah, so don't think about this so much as a particular person. Think about it as like a role. So for instance, if we were to imagine a program that represented a point of sale system, the roles might be customer, cashier, bank, marketplace. Those might be who they are. And they're not a specific customer. It's the idea of the customer. So kind of the way to think about it is that we're going to be describing an interaction between prototypical Alices and Bobs. And when we ultimately run the program, Alice will be one particular person and Bob will be another particular person. And the program, when it talks about Alice, it says, these are things that Alice does. And when it says Bob, it means these are things that Bob does.
Got it. So after we deployed it, I could come in and I could be the Alice user and you could be the Bob user, and it's going to execute the way we told it to. Okay, got it. I'm
exactly.
with you.
Now, basically the way that we do this is we give a JavaScript array that is the name. And then this right here is what we call an interaction interface. I'll talk about this in a moment. Now, this function right here is our program. And so it's going to take 2 arguments. And the arguments are going to be for each one of the participants. Now, inside of here, we're going to write our program. And when we're done, we can write exit if we want, or we can just stop. Now, I'm actually going to leave my program like this because it doesn't do anything yet, but we can still run it because it's a valid Reach program. And I'm just going to show you what it looks like to run this program. So I'm going to go down here, and I'm going to run the Reach compiler, and I'm going to write compile index.rsh. That's the name of this file. So what it does, if you are doing this on your own, the way that you get the compiler, you can click on install and initialize. And it will talk about, okay, you can install it by running this. If you're on Windows, you'll follow these instructions. And For some reason, it took a really long time. I find that normally my computer is super slow when I'm sharing video, so maybe that's why it was slow.
It's probably because we're doing Zoom. Yeah.
Yeah. So anyways, so it went off and it compiled and it prints out all these messages about how it did the compilation, how it did some verification and checked some theorems. I'll talk about those in a moment. But now, like, what happened? What did it do? What does it mean to compile the program? Well, now in this directory, I have this new directory called build. And inside of build, we can see that it produced a whole bunch of temporary files. Now, when you run this, if you're not going to run the development version, then you're only going to actually have one file, and that's going to be this one right here. And that is a JavaScript file that you can interact with to run the Alice role and the Bob role. All these other ones are internal details that the compiler does. And probably the most interesting one for you might be the Solidity file. You can read the Solidity for the contract that we wrote. Now, our contract isn't interesting, so we're not going to look at these. But I just wanted to point out that this is what happens when we're in the compiler. Now, so
anything front end based here, or is this all basically just contract stuff right now? There's no app scaffolding or anything yet.
Correct. Right now, there's no app scaffolding.
Cool.
What we'll do is we'll write that in a moment. So let me just split the screen here. And what I'm going to do is I'm going to open up what we're going to write as our front end. So what we'll do is the main thing that we want to do is we want to load the Reach standard library and then load that build file that got generated. And we call that the backend. The way that you think about this is that you are going to have a program that describes the behavior of Alice. And the Alice program has to interact with the blockchain, through like Web3 or Ethers or whatever. But you don't want to write that code because you don't want to learn about it. And also because if you directly tied to Web3, well, then now you're stuck using Web3. And if you use Ethers, you're stuck using Ethereum. We're going to write a program that does not depend on what blockchain we use at all. Like, we're going to write a program that will work today on Algorand and Ethereum right off the bat. Now, this code is a little bit boilerplate, so I'm going to copy something in. So what I'm going to do is, it's just that it's very common to kind of want the same things. So what I'm going to do is I'm going to initialize the standard library. This is the Reach standard library. I'm going to say that I want to have an initial balance of 10 units of currency. And then I'm going to make two test accounts, the account for Alice and the account for Bob. Now, this program that we're going to write is going to be a program that uses an internal private DevNet. We're going to hit run, and it's going to start up behind the scenes a totally fresh Ethereum dev node, make these two accounts on it, and then run it. If you were to write the web version of this program, you wouldn't say new test account, you would say connect to MetaMask, basically. And then it would just use whatever your browser's thing is.
Got it.
So that we can see what the program does, we're going to have the program start off by looking at what the balance is for each participant. So we're going to define an asynchronous function that gets the balance of Alice and then of Bob. And what we're going to do is we're going to print out what these are at the end of our program. So I'm going to put the program in the middle. And then at the end, what we're going to do is we're going to get the balance afterwards, and then we're going to print it out. So program goes here. Okay, so we're going to write a program where Alice and Bob do something, and they change the amount of money that they have. And so it'll say, before Alice has this much, after Alice has that much.
So up top is basically our app. This is the kind of like a script we run, and that's considered like the app. And then down below is sort of like the behaviors that these sort of actors will take.
Exactly.
The thing below is kind of like our smart contract, and the thing above is kind of like our app. Is that right?
Yeah, that's a good way of thinking about it. Another way to think about it too is that the thing on the top is totally normal, boring JavaScript. The only thing that's slightly interesting about it is that you get to use our standard library that abstracts away the difference between different blockchains. You call parse currency rather than
big numbers and a lot of the stuff that you run into. Yep, got it.
Now, the one thing though that is a little bit different is that this right here is not exactly the smart contract, because it actually includes things that are not only the smart contract. So let's define what we're going to do a little bit. So what we'll do is we'll make it so that in this program, Alice and Bob are going to play rock, paper, scissors, my favorite game. And the reason that it's a fun game is because there's no real way to win it. You know what I mean? So it's not like a solved thing like tic-tac-toe or chess or something like that. And so what they're going to do is that they're going to bet on who's going to win this game. So what we'll do is we have to first determine the wager that they're going to bet. Now, what we could do is we could just hard code it in. We could like put inside here a variable that says, the constant wager equals 10. And now we're going to be saying, okay, they're always going to wager 10 Ethereum. But I mean, that's a little bit too dear for me. I can't afford 10 Ethereum. So what I'm going to do is I'm going to make it so instead, Alice is going to do something at the beginning of the program. We're going to write alice.only and pass a JavaScript func. That's a JavaScript function that takes no arguments. Now, what we're doing right here is we're saying something that Alice does on her side of the contract, on her local machine that Bob doesn't do. And what she's going to do is she is going to define what the wager is. She's going to call interact.wager. Now, what's interact? Interact right here refers to this object. So this object is Alice's interaction interface. It specifies an interface between her and the backend contract. So what we'll do is we'll go in here and we'll say that this has a field named wager, which is an unsigned integer. Hold on one second.
This is it's like a totally different paradigm about thinking. Like as I'm going, I'm like kind of extrapolating this out and figuring out how this might fit in with my dev. It's like you guys said, it's a level of abstraction up, and it's just thinking about these interactions in a completely different way. And you almost need to see it all done first before you can even like do pattern matching. So I'm excited to keep seeing this. This is neat.
Okay. So by putting this thing right here inside of this interaction interface, what that means is that over here in this code, Alice has to provide that information. So let's write a little bit more of this program. Now notice that we're constantly going back and forth between these, and that's typical because right here is like our application, and right here is the part of it that interacts with the blockchain, and you really can't separate those two. But we don't want to include this logic over here because we want people to have different choices, right? So the Reach programming language is based on JavaScript, but we are working on a backend that compiles to Go. So you could write this part of the program in Go. You don't have to write it in JavaScript. Okay, so what are the steps of the program? So the first thing that we want to do is we want to define the contract for Alice. And so we do that by writing the account Alice .deploy, and she's going to deploy the backend. Now, what is the backend? That's the thing that Reach compiled right here. And we'll write contract Bob, and that's going to have Bob's account attach to the with the backend to whatever Alice deployed. So this deploy, think of that as launching the Ethereum contract. And what attach does is it connects to that. And so this get info basically says, I launched it and I launched it at this address and so on. Okay, so now we have these contracts and we have the deployed version and the attached version. So now we have to run them. So the way that we're going to run them is we are going to write await promise.all. And this is just normal JavaScript, promises and whatnot. And when we compile our program, the backend is going to provide a function for Alice, and it's going to provide a function for Bob. We can actually look at these right now. Let me just close this for a second, and let's look at this build directory, and we can look at that build file. And what it does is it defines a function named Alice and a function named Bob. Now notice that these functions don't do anything yet because we haven't compiled our program to actually do anything, so they're just empty. But those functions right there are what it means to compile a Reach program. Now they're going to take in as an argument the standard library, which we defined. They're going to take the contract that they're supposed to attach to, and then they're going to take the interaction object. And then Bob is going to do the same thing, the standard library, his contract, and then the interaction object. So now what is the interaction object? Well, it has to define what the wager is. And so now here, I'm going to say that the wager is, they're just going to always bet 1 Ethereum or 1 whatever the currency is. So because I put wager right here, I'm specifying the interface that this participant has with its front end. And then this code allows us to interact with that and grab it. So now what Alice is going to do is she's going to publish this information. And she's going to pay that amount to the contract as well. So what's going on here? So in a reach program, the key thing that you think about is what do individual actors do and what information do they share? And sharing is called publishing. They don't send information to a specific party because that's not how the blockchain works, right? The way that the blockchain works is when you provide something on the blockchain, it's now publicly available to everyone. So we use the word publish to talk about that. Now, when we say pay, what is it paying? It's paying the smart contract itself. So this is transferring resources from Alice into the smart contract. Now, what we can do after we transfer this money is that we're now inside of the smart contract, and we can write down constraints on when this is allowed to happen. And when we're done checking all of those constraints, we'll commit. And in this case, there are no extra constraints to do. Okay, so now at this point, we have added 1 step to our program. Alice figures out what she wants to wager, she publishes it and pays it. And so now let's compile the program and see what happens. Sound good?
Sounds great. So the commit, so the publish, I'm wondering which one of these is like the transaction underneath the bits there.
Yeah, underneath the covers, what is what?
Yeah.
Publish is like calling a method.
Okay.
And commit is that method finishing without calling revert.
Okay. Okay. And pay is just attaching some value to it within the same call.
Exactly.
Cool.
Yep.
Got it.
And the thing is that notice that we don't specify anywhere what's the state of this program, what's the name of this method, whatever its parameters, all that is going to be derived automatically by the Reach compiler.
Got it.
Okay. So I'm going to go down and compile, and I'm going to tell you that there's going to be an error. And as I said, it normally compiles a lot faster. And like I said, I think it's because something is really slow about my machine because of the zoom. Okay, but we expect there to be an error. And this is what the error says. It says, invalid binding in only on line 12, secret identifiers must be prefixed with underscore. Did you mean to declassify? So this is an opportunity to teach you about something else that Reach does. So one of the things that Reach does is it uses what's called an information flow security system to guarantee that secret information of individual participants is not shared without explicit declassification. So we initially assume that everything inside of the interaction interface is secret information that Alice wants to keep only to herself. And what we're doing right here is we're assigning wager to be this interaction stuff, and then we're publishing it. And that is not allowed because it needs to be explicitly declassified. So we have to explicitly type into our program, declassify this. And now it's going to allow us to continue because we are going to explicitly acknowledge this is information that I want to be allowed to share.
It's kind of like making it payable in Solidity. Basically, it's explicitly safe and making sure you don't do what you don't mean to do. And you explicitly have to say, okay, this thing either needs to be declared as public or needs to be declassified at some point to get to be published. That's cool. Got it. And this, again,
Exactly.
Leaning back on safety, you kind of have these like sort of kind of safety concerns that you can lean up against and kind of be very explicit about making this declassified. I got it. Cool.
Exactly. Now, I made that change and I compiled again and I got a new error. And this new error says, verification failed, balance assertion. And the theorem, it says theorem formalization, V1 says that 0 is supposed to equal V10. So what's going on? It says that, well, if Alice's wager were the number 1, then your program could be broken. And what's broken about it? The thing that's broken about it is that Reach guarantees that when your program exits, there is always a zero balance on your contract. Because if there's not a zero balance and your program is over, then that means those funds are locked away forever. I don't know if have you ever heard of any contracts that were broken by locking their funds away forever?
I think a few, yeah.
Yeah, I think I've heard of that too. So what Reach does is it guarantees that this never happens. And so it's going to look at your program and say, aha, well, what if wager was 1? Then this could happen. Because, of course, wager ends, we pay, but we don't take it out. So let's continue with our program to make it so that this error goes away. So what we'll do next is we're going to say Bob does something. And what Bob is going to do is he's going to call an interact function that's going to be called accept wager. And he's going to be sent the wager. And then if he agrees to it, then he's going to pay the wager also. And just for simplicity, so we can run the program, I'm going to do something that doesn't really make sense. I'm going to have it so that we're going to transfer 2 times the wager to Alice right away. Now this like
she just basically wins. Yeah.
Yeah.
What we'll do is we'll get in and we'll write the logic, and it will pay it out. But the point is to have it paid out by the end, just so everything compiles. Got it.
Exactly. Just so it compiles. But now if we run this program, we're going to get another error. So like all good programming languages, the point of Reach is to give you lots of errors so that you don't have to be clever. It will find the errors for you. Okay. Now the error says, it says, accept wager is not a field of Bob's interaction interface. Because we acted though Bob had this function right here, but we forgot to add it up here. So let's go do that. So we'll write that part of his interaction interface is a function that's called accept wager. And it's a function that takes a uint and returns nothing, and returns null. Okay, so now we'll run. And it's now going to be satisfied. Okay, so it ran, everything's fine. And now what can we do from here? Well, first of all, I want to point out that notice that we wrote, transfer 2 times the wager to Alice, and it satisfied our theorem prover. It figured out that that means that the balance will be 0. Now, this is not something really simple that just says, oh, like, well, it's the wager plus 2, so that must mean it's the same 2 times. This is a full formalization of math. So if we made a little mistake, like what if we did subtract 1 there? Well, it's going to tell us that this is wrong, because that means that, well, what if wager were the number 1? Then you're going to be missing something. So I want to get across the idea that we're not doing a subtle analysis of your program. We're doing a very sophisticated analysis of your program, where we're analyzing the exact logic of every single mathematical operation you do to guarantee that they're all consistent with the correct behavior of any smart contract. Okay. So now let's go back to our front end, and we'll try to run it. So notice that we've got Alice, we've got Bob here. So let's see what happens when we run the program. So here I'm going to write run.
And Bob doesn't need to do anything with the accept wager stuff. It just, since it's a function and it's there, it'll just happen.
No, we made a mistake, and it's gonna catch it. It's gonna catch it. But you're really smart. You must be a good programmer. So we ran run, and now what's going on behind the scenes is that Reach is creating a Docker image that for our application, it's creating another Docker image for a test node. It's loading up that test node. It's connecting them together and then running, so that all of that scaffolding that is, a little bit painful to learn how to do is done automatically for a Reach programmer. They just write Reach run, and then it goes. And now notice that we get an error. It says, interact.accept wager is not a function inside of the module Bob. So we got to go back and fix that. But you were really smart. You knew that. So I'm going to go up here and I'm going to say accept wager. And I'm just going to write a function that takes in wager. And I'm going to say console.log. And I'll just say Bob accepts the wager. And maybe we'll write out what it is. There's a function to format it nicely that is called format. Now we'll run it again. And it goes through and it, rebuilds our Docker images. It connects to the same network that was there before because, it's a little bit, it like leaves them persistent if it can. Now it runs. And, it's connecting and it says, okay, Bob accepts the wager 1. Alice went from having 10 to having 10.99999. That gas always gets you. And Bob went from having 10 to 8.999. So now behind the scenes, what happened is that Reach generated the smart contract and it generated the program. Let's look at the smart contract that got generated. So this right here is the Solidity program that got generated. I'm going to scroll through it. So, it targets the ABI encoder there. Reach guarantees that no matter what program you write, the state is always a single uint256 for storage, because it basically performs a Merkleization of the state of all of your program, and it will compress it into a single hash so that you will have minimal gas costs for storing your persistent state. We define a constructor. We go through, right here is the function M1, which is the first thing that the program does. That's message 1. And notice that there's a require statement here that says the value of this message has to equal the argument v3. And what's v3? v3 is the only argument that's there. Now, what's going on here? It's saying that whatever value you publish, whatever value you pay has to be equal to the thing that you published. So it's checking to make sure that the pay amount is actually this number that you said it was. You're not allowed to publish something. You're not allowed to say the wager is 10, but actually only submit 9, or else it'll be rejected. Then what it does is it updates the state and is ready for the next message. What the next message does is it starts off by saying, am I in the right state? Is the state in step 1, and are this variable right here, SVS, is it what the correct things are? And SVS, if we were to go look, it records who the identity of Alice is, and it records what the wager was. Then it's going to check that Bob has transferred a value that's equal to what was saved away that we checked in the current state. And then it's going to transfer using safe multiplication 2 times that amount to whoever V2 is. Now, you don't need to look at the details of these things. I'm only showing them to you because, you're a Solidity expert and then you understand these things.
Not an expert, but I like it.
The Reach programmer doesn't need to know any of this. But now, what's even better than this? What's even better than this is that Reach actually also generated a teal version of this program that will run in Algorand. So let's open up that and go to it. So by the way, this right here is the backend function that got generated for Alice. So this is like the output of a compiler. So it's kind of gobbledygooky. So I won't really bother explaining it. But it's relatively short. If we scroll down a little bit, we get down to this variable that's called algo. And I don't want to explain too much about how Algorand works. But basically, when you write an Algorand program, you're not writing one smart contract. You're writing like a family of smart contracts that all interact with one another. And they're all written in a stack-based assembly language that's very similar to EVM. And so what happens here is that Reach generates this extremely long assembly program that is basically 5 different smart contracts that all work together to implement the behavior of this program. And we can make it so that Reach, when we call Reach run, we can have it use Algorand instead. So I'm going to write Reach connector mode equals algo, and then I'm going to run. And then now it's going to go do the exact same thing as before, except that rather than starting up an Ethereum dev node, it's going to start up an Algorand dev node. And I anticipate that this will take a lot longer than the Ethereum one because Algorand doesn't have it actually doesn't have a dev node. So this will only run at like the normal network rate that Algorand runs at, which is like 5 seconds per round. And each round can have many transactions, but our program has to have 1 transaction per round. So it's going to take like, our program has, I guess it has like 4 steps. So it's going to take at least 20 seconds to do. So I'm just going to actually minimize this and go back to the program and we'll see it finished later. Okay, So we now have the basic demo of things, but of course, this is a dumb program because it doesn't actually do the rock, paper, scissors thing that I said that we were going to do. So let's modify the program so that it really performs, a game of rock, paper, scissors. So what we'll do is, Alice will publish the wager, Bob will accept the wager, and then after he's done, what we'll do is that now we're ready to go. So then now they can say what they want to do. So I'm going to write Alice.only.
And what's neat here is you don't want to declassify the moves until each person has made their move. That's
exactly.
Cool.
Yep. We'll show a mistake here.
Cool.
Okay. Oh, notice by the way that it finished down here, and it says, Bob accepted the wager. Alice went from 10 to 10.691 because the gas fees are very different on Algorand, and Algo, and then Bob went from 10 to 8.995.
Cool. So same execution on completely different chains with completely different virtual machines that kind of run those. That's
and
very cool.
It's actually a little bit unsatisfying because the output is exactly the same, basically. It's like the most boring demo. Like, look, it does exactly the same thing as it did before. Okay, but of course, behind the scenes, there's a lot more exciting things happening. Okay, so let's modify this program. So we're going to say that Alice is going to say her move. And by the way, we normally write we write secret variables with underscores. And the compiler enforces this. It says that you have to have, if you have a secret variable, it's got to start with an underscore. And it starts with an underscore, it's got to be secret. So we're going to say interact, and we'll say get hand. And then what we'll do is, well, how do we make it so that they both do this? So, I mean, what we could do is we could then say, okay, well, Alice has that hand, and maybe we'll call it hand A and hand B. And this is what Bob does, okay? But now one of them has to do something, one of them has to actually publish it first, right? So then how do we actually publish it? This is actually kind of a problem because imagine that Alice published her hand first. Well, then Bob could just go look at it and then publish the one that he knows is going to win. So actually, this program really can't work. So what we'll do is we'll write, but I'll show you how Reach helps us see that it can't work. So first of all, if we try to publish hand A, then it's going to error. And you're becoming a Reach expert. So why is it going to error?
It's got to be something with the commits or something like that. I don't totally understand yet, but I'm following along.
It's going to error because we didn't declassify it.
Oh, that back to the declassification thing. Got it.
Yep. It's going to error because we didn't declassify. So when we run reach run, it's going to say. Are we going to
have to do like a commit reveal here? Like, is there like a whole pattern of committing hashes and then checking? Neat.
Yeah, exactly. So we're going to have to do something like that. So when we try to run this program, it's going to give us two errors. First, it's going to say that get hand isn't in our interface because we forgot that. And it's going to say, see, it says get hand is not a field of Alice's interaction face. Did you mean wager? Because, it does its best to help you, but some people can't be helped. Okay. So what we really need to do is we need to do a commitment pattern. And doing a commitment pattern is kind of hard. So naturally, there's a library for this. So we're going to say make commitment, and we're going to make a commitment to hand A. Now, when you make a commitment, normally the way that you do that is you hash the thing that you're committing to. But the problem is that if you hash the same thing over and over again, then it's always going to be the same, right? Because if I hash rock, then it'll always be the same thing. So Bob can actually just check that. So what I need to do is I need to hash rock and some random number. And then we call that the salt. So Reach has no facility for getting randomness because it doesn't want to take on that responsibility. It puts that on you, the user, so you have to make it so that getting randomness is part of your interaction interface. And Reach will help you do this. And then what make commit is going to do is it's going to return you two things. It's going to return the commitment, and it's going to tell you the salt. So we're going to write make commitment interact, and then we're going to get the thing that we want to commit to, and then that. And then what we'll do is we will declassify just the commitment. And then that declassification of the commitment, that's the thing that we're going to publish. Okay, now to do this, we need to add some stuff to our interaction interface. So let's go do that. So it turns out that both Alice and Bob are going to have this same behavior. So what we'll do is we'll make an object that is their shared behavior, and we'll call it a player. And remember, this is just like JavaScript, so we can make an object that has a lot of behavior. So we'll write constant player, and it's going to equal, well, we have to be able to provide randomness. So Reach has a library that's called hasRandom that you include. And this just basically says, this interaction interface has the ability to provide randomness. And then it has this function that we're going to call getHand, and it will take in nothing, and it will return a number. Because we're going to
randomness underneath, is that like using an oracle or using its own commit reveal with block hashes or something? Or what you
so
basically have to implement?
This randomness right here is in the player interaction interface. That means it's something that happens entirely locally. It doesn't happen on the blockchain. It only happens inside of each individual client. So essentially what that means is that we're going to have to include inside of these functions right here the ability to get randomness. So go up here into our JavaScript code, and we'll write ... player. And over here, we'll write ... player. And we'll define the shared player interface. And the shared player interface is going to use the standard libraries hasRandom. And what that thing is going to do is it's going to use ethers to get cryptographically safe random bits.
From where? Like, how does it, where?
Basically, this is kind of like an operating system thing, but you have
okay, so local, still local to the machine, definitely not okay,
totally local,
okay.
Totally locally.
So we're thinking that this is almost like a state channel opened up between Alice and Bob, and they have their own channel, and they're kind of committing, but they're not committing on chain, they're committing to each other, and the randomness they use is just their own local box randomness. It doesn't need to be deterministic or on chain or anything like that.
Correct, because it's just to get salt to distinguish their hashes. And if you didn't trust this function, then you could just write it yourself, connect to a hardware random, generator, things like that. Now we're going to write our getHand function, which is going to be an asynchronous function that's going to return something. Now, just for convenience, let's have it return, we got to have it return something. We'll represent rock, paper, scissors by like 0, 1, and 2. So let's have it just pick something randomly. So we'll have it return, a random number between 0 and 3. And so, of course, we could, if we wanted to, make it so that we allow the users to like type in what they want, but let's just not bother with that.
And is that kind of the app level interaction right now is basically STD in and out? Like there's not, I think we've kind of talked about this, and we should kind of transition this eventually, but like React and stuff, like say we wanted this rock, paper, scissors to be in React. Eventually you would put that in, but for now we're just going to kind of from the console do the.
Yeah, I'm going to go over here to the tutorial for just for a moment to just like point out this function in the tutorial. So if we go to section 2.9, that's called web interaction, then you'll see the code is a lot bigger, right? Because a React program is longer. But right here, see, we're going to define the getHand view, and the getHand view right here is going to provide a getHand function. And this getHand function is going to say, set the state to getHand, and when you're done, resolve this promise and take that hand and convert it to an integer. Now, what is the getHand view? The getHand view.
Probably just those 3 buttons that give you a number for each one if they click it. Yep, got it.
It's just those 3 buttons. So when you click the one that says rock, it says play hand rock. When you hit the one that says paper, play hand paper. Okay, very, very straightforward.
And that React stuff really, there's not a lot of the React stuff that's generated with Reach. It's just showing you that if you wanted to take this up a level to React, here's how you would implement it.
Yeah, and I want to emphasize that this box up here, when we're writing the front end, There is absolutely nothing special about it. It is totally normal JavaScript. There's nothing in it that says, I must be using React, I must be using the command line. It's just plain JavaScript. You can use any framework you want, any paradigm, anything like that. Like this could be hidden inside of an app, for instance. Like when I say an app, I mean like a mobile app, you know what I mean? That's not really on a browser.
Got it.
Okay, so we've got our getHand function. We have Alice commit and publish it. And now we want Bob to do the same thing. Now, the thing that's interesting here is that it turns out that actually Bob, he could just directly publish his hand because Alice has already committed to her hand being one particular thing, right? Because she can't change what she already did. So Bob will publish his hand and commit to it. And then Alice will come back. And what she'll do is she's now going to declassify her hand and the salt. So she's going to call declassify on both the private hand and the salt. And then what she's going to do is she's going to publish those. She's going to publish her hand and her salt.
So is each publish here a transaction, or
Yep.
are these just going between? Okay, so each one of these are on-chain. Got it. Cool. So I mean, it literally is a commit reveal, and that second publish is the reveal. And we just didn't need to have Bob reveal. He basically just reveals. He doesn't have to commit. This is cool. I think I'm following you.
Yep. And now we're going to write check commitment, and we're going to check that commit A is a commitment of salt A and hand A. And then if it is,
your hash works out. Got it.
Now, if it is, we can figure out who the winner is. And how do we figure out who the winner is? So first of all, we'll transfer to the winner. Okay, and we'll say, well, the winner is what? Well, now we got to use like math. We basically have to figure out like, okay, well, if it's rock and rock, then this is very annoying. Okay.
Hopefully you have a copy paste somewhere for this one.
Yeah, I'm just going to copy and paste that.
Perfect.
Okay. So here's the answer. So
gorgeous.
If you take hand A and you add it to 4 minus hand B and you %3 that, then what it turns out is that if basically the way to think about this is it's like this enumeration right here, that 0 is when B wins, 1 is when there's a draw, and 2 is when A wins. So let's actually call this outcome. And then we'll say, who is the winner? We'll say the winner is equal to, if the outcome is equal to B wins, then, actually, you know what? Let's write this a little bit differently, because we want to handle that draw. So what we'll do is we'll transfer, let's transfer 2A times the wager to Alice, and we'll transfer 2B times the wager to Bob. And then what we'll do is we'll define these variables at the same time, 2A and 2B. And what we'll do is we'll say if the outcome is equal to B wins, then Alice will get 0 and Bob will get 2. But if the outcome is A wins, then Alice will get 2 and Bob will get 0. And otherwise, they'll both get 1.
It's tricky,
right?
But I got you. I'm following you.
Cool. So now let's run the program and we'll see what happens. There are no planned errors right now. So if there's an error, then it's a genuine mistake that I made.
One of the things to really point out is like, yes, this is tricky, but this is just rock, paper, scissors. This has nothing to do with reach.
Yeah,
exactly.
Okay, so I made a mistake, which is that I forgot to write a commit right here after she published.
So a publish is like preparing the transaction and commit sends it. So you can publish multiple transactions and commit them as a group, or you guys are saying I'm like pattern matching and it's almost hitting it, but not quite.
Think of publish as being like a method call on the contract, and commit is that method returning.
Got it. Okay. So you're kind of crafting the call data and then committing it is, wait. So the method is actually, the publish actually does call the contract, the commit makes sure it returns. And if it doesn't, does everything revert, or like, is it atomic as we're thinking of it in Solidity, or what if it doesn't work? You get to the commit line and everything blows up?
If the code in between publish and commit can have arbitrary checks. And if any of those checks fail, then the computation is reverted. And now if you're asking like, what if I literally don't include commit in my program? Then the Reach compiler will complain and said, you forgot commit in your program, put a commit right here.
Okay, it's kind of like an await, is that right? Like it's kind of waiting
Yeah,
for
it's
everything?
kind of like that. You can kind of think of it as it's a note to the Reach compiler that I'm done with the contract side. Now go back to letting individual participants do stuff.
Cool, got it.
So we ran the program, but I mean, we didn't really like, it just said, it looks like there was a tie, but we don't really like know why there was a tie. Because we wrote a bad front end. we made it so our front end like doesn't do anything. So let's modify our program a little bit so that we can actually like see what's going on, okay? So what I'm gonna do right here is I'm gonna make it so our player function is gonna take an argument. So this one will take the argument Alice, and this one is gonna take the argument Bob. And then who will now be a function that takes, sorry, player will be a function that takes in who. And then what we'll do right here is we'll say console.log, and we'll say who plays the hand, and then we'll write down what hand they played. And so we'll say const hand equals that, and then they'll return the hand. Now let's run again. And so we'll be able to see a difference. Now notice that like we improved our front end without making any change whatsoever to the Reach program because we don't need to. So it's down here running. And it says she plays the hand 1, Bob plays the hand 0, and that means that Alice won because 0 is rock, 1 is paper. So that means she played paper and he played rock. And if we wanted to, we could, improve this. So I'll say, display the hand. And what's display? Display is, actually I'll call it hands. And it'll say rock, and then paper, and then scissors. And now I'm just writing a JavaScript program. You know what I mean? I actually kind of forgot that there was a Reach program behind the scenes here. I kind of forgot that I was working on Affinity. Now I just get to think about the business logic of whatever the thing that I care about is. In this case, I care about rock, paper, scissors because I'm a maniac who loves rock, paper, scissors. But if you care about something that really matters, like decentralized loans or something like that, then that's what you would be thinking about. All right, so here Alice plays rock, Bob plays scissors. And so that means that Alice won again. Alice is really good at this game, apparently. Now let's go back to the Reach program for a little bit. Now notice that we already established that what Reach does is it guarantees that there are a whole bunch of things that are not wrong in our program. For instance, it guarantees that we don't try to overspend or underspend. Like here, let's imagine that we made a mistake and we made it so what if I accidentally made it so that if there's a draw, Alice gets too much money? What's going to happen here? Well, the thing that's going to happen is that the compiler is going to say your program is broken. It's going to say that I tried to check to make sure that this transfer right here had enough money, but I was wrong. And it's going to explicitly tell us what if wager was 1, and what if someone played rock, and what if someone else played scissors? So let's look. It says right here that your program could be broken. We got to scroll quite a bit. It says,
so is
what
it
if
like fuzzing too? I mean, like that
No.
stuff is like way over my head, probably. Like doing that kind of like testing is probably something that I don't even know how it works, but it's not like fuzzing where it's just trying things. There's some kind of like formal verification that happens.
Right. It takes your program and turns it into, here's a way to think about it. It basically takes your program and turns it into a linear algebra problem. And if you remember anything about linear algebra, then there's this algorithm, Gaussian elimination. You just do Gaussian elimination and you can just find the values of all of the variables. It basically does that, but for a more complicated kind of mathematical set of equations. And so it says, what if the wager were 2? And what if Alice's get hand was 4? And what if Bob's get hand was 4? I.e., what if there was a draw? So it discovers that your program is broken when there is a draw. Isn't that remarkable?
That's cool.
We can fix that. But we can, it actually, behind the scenes, it's verifying way more than this. Like, notice that right here, we have this check commitment. But what if I like lied? You know what I mean? What if I lied and made it so that rather than publishing the actual hand 0 right here, what if what I really did is I like always published rock? And this always publishing rock is standing in for the fact that like maybe I'm going to look at what Bob did and try to figure it out. Okay. Well, there's going to be a different error here. The error is going to say this commitment right here might not always work because we don't actually trust Alice. So this tells us a little bit more about how Reach works. When it verifies your program, it verifies it in a whole bunch of different modes. In one mode, it doesn't trust anybody, and it says, did you check enough to make sure that if everyone was untrustworthy, you would verify everything? But it also checks it in another mode that says, what if we did trust everybody? Would everyone meet their obligations? And this is an example of a program that would fail because it says, in honest mode, this require that comes from the standard library that you called at line 49, this is line 49, the check commitment line, that theorem right there could fail because Alice could have returned 38 and random could have returned 719, whatever that, why it does that, you know, it's just some number. It says if it returned these two things, then that means that this commitment wouldn't be the right one, okay? So it verifies that about our program. And we can actually verify even more. So let's add one last thing, and this is really the last thing that we're gonna do. Actually, yeah, I guess this is the last thing we're gonna do. What we're gonna do is we're actually gonna prove that right now we didn't make a mistake and we didn't accidentally reveal this hand early, because we're kind of nervous that maybe Bob could figure out what Alice's hand was from this commitment. So what we're going to write the theorem that it is unknowable to Bob what Alice's hand or salt is. So this is a little bit of a weird reach syntax.
Going with your declassification already, once you have that abstraction, you can have a function to say, has this been declassified yet? Or is there any way of this actor knowing this other actor's private data? That's cool. Like this access model that's sort of built in.
Yep. And the way that it does this is, again, it's not like trivial. It's not like, it doesn't literally just say, has this thing been declassified? It actually, I accidentally wrote B, but I meant to meant Bob and Alice. It doesn't just say, has hand A been declassified? It will actually, like, if we didn't publish hand A, but we actually published like hand A plus 17, then it's going to say, aha, they could know that you did plus 17. They could subtract 17 and then figure out what your number was. And so notice that it came back and it said that I verified the theorems. So it worked. So anyways, so this is what it's like to write a reach program. You, at no point do you ever think about what is the state of my computation? What state transitions are valid? What methods do I want to create? And how do I know that they're going to write? And should I put this in persistent storage or should I put it in memory? And oh no, I used more than 16 variables. You never think about any of those things. All you do is you think about the business logic of what you want to do, what each actor does, and then what Reach does is it automatically figures out what the state of your computation should be, and it will derive a smart contract for that computation. And it does it in Solidity, and it does it in Teal, and you know, we have on the pike more networks that we're going to be supporting soon as well.
I think, yeah, so talking about like the 16 variables stacked too deep, like you as a developer run into this all the time in Solidity. You have these problems, you have these kind of issues that arise, and you're saying like you won't have those with Reach because Reach will kind of take care of them. But then it kind of like makes me worry about, well, like what is going on? Like how does that work, sort of? So maybe, so I would say that like in this example, kind of like going back to like the Alice and Bob example is a perfect nail, and Reach is a really great hammer for that. What are maybe some other things that you can build with this that are a different model than just Alice and Bob playing rock, paper, scissors? Like you mentioned loans earlier. Like, could you build a lending platform with Reach and who are the actors and how does that work?
Sure. So let me just talk about two things
Yeah.
as kind of as like the road to that. So the first one is that just recall that this front end program that we wrote, like it's just normal JavaScript. So if you are, I kind of feel bad that I didn't show you the beautiful web version, but I don't want to really get bogged down in that. And you're already a React programmer, so you can think about how to do that. And if you want, you can go look at the documentation and it will walk you through building that. Now, I think your second question is best answered by going to a different part of the documentation. So if we go to the docs, the way that they're organized is that we start off with a very brief overview of what Reach does. It presents a program that's even simpler than rock, paper, scissors to show you the different steps of what it does. What the tutorial does is it writes this program that we just wrote, except that it does it over the course of 8 hours as you painstakingly look at every single design decision. The goal of our documentation is not to turn you into a Reach programmer. The goal of our documentation is to turn you into a dApp developer who understands what all the design issues are with decentralized applications. And of course, we use the best tool for the job of writing dApps, which is of course Reach. And so we don't just say, oh, go use the commitment pattern. We talk about the issues about why commitments patterns show up in so many different things. Now, after you go through the tutorial, we have what's called the guide. And I think the guide is kind of the answer to your question of what's going on behind the scenes? How does it work? And we try to answer questions like that. So, what is even worth verifying? Something that I didn't talk about is like, how do you write like while loops? And how do you deal with this other issue that's called non-participation? So one of the things that you always have to think about when you're developing a dApp is like, what if Alice just decides that she's not going to publish this message? What if she just like walks away? What's going to happen there? So Reach has facilities for dealing with that too. And it talks about some of the ways, some of like the algorithms that Reach uses to work. And that's kind of where you can see like, oh, behind the scenes, like how is it making it so that we avoid the 16 character thing? I mean, it's the 16 variable thing. Okay, but then separate from the guide, we have this other thing that's called the workshop. And the idea of the workshop is, if the overview is like week 1 of a college class, and the tutorial is like your first big project, the workshop is basically like your homework projects that you're going to do for the semester's work. And through here, what we do is we walk through the design ideas that you would have to do something like using a hash lock, which is a common idea, how you would do something like a relay. And over time, and we have things like, how you would make a Guardian account, or how you would do periodic payment. And in the future, we'll have things like a secured loan or an Oracle or an auction, things like that.
Can we click on like rental agreement real quick just to see those actors?
So this right here has just a very short discussion of it. So I'm just going to kind of read it out loud. It says, in this workshop, we consider a scenario where Alice and Bob are engaged in an indefinite rental agreement, where they both made a security deposit to be given to whomever leaves the arrangement first. At some regular interval, both participants submit whether they would like to stay or leave. If they both decide to stay, then they wait for the next round. If they both decide to leave, then they both get the deposit. But if only one wants to leave, then both deposits go to the participant that wants to stay.
Yeah, I get it. I see like when I'm going back to fitting the mental model, like going back to, oh yeah, we're talking about how Alice and Bob are interacting and they're doing it in steps where they're committing. When you think, oh, it is kind of like these steps, then I can think of a rental agreement in terms of those steps. It's like, it's sort of like when I first started learning how Ethereum works, right? And the gotchas and how you kind of have to think about crafting an app. This is a little bit different. It's a new kind of paradigm of how you would craft your dApp. And I think you guys have seen how to build Ethereum apps traditionally and sort of like figured out what that looks like and kind of tried to create a layer of abstraction on top of it. And it makes sense. Yeah, I can see how that would work. So how would the loan example work? So loan would be like,
let me tell you something other than a loan, actually.
Okay.
So we have an extremely high standard for ourselves with the documentation. So I only want to have things in the documentation that are fully explained with a lot of detail. So I'm going to show you now something that is on on like basically our development side that's not quite ready yet. And I think it's a good example of the kind of thing that you're talking about. So this program right here is a raffle. So the way that the raffle works is that the different roles are the sponsor of the raffle and then the category of players. Now notice this looks a little bit different. Rather than saying player, we say this is a class. The idea behind a class is that it's basically a participant where this participant can attach to the contract many, many times. There can be many players. And so rather than saying Alice and Bob is one specific people, like once the program starts, Alice is one thing and Bob is one thing, here a player is an arbitrary number of people. Okay. Now the way that this program works is that the sponsor decides the parameters of the game, of the raffle. They set what the ticket price is, what the deadline is, and then what they're going to do is they're going to save some randomness. So they're going to save some randomness that's going to be included at the end of the competition to figure out who the winner of the raffle is. Then they're going to publish the ticket price and the deadline. Okay. Now we're going to look. Now you're going to see something that is extremely different than anything you saw before. So I can only vaguely describe it. So what we're going to do right here is we are going to do what's called a parallel reduction. So if you've ever heard of like map reduce, which is a way of doing massively parallel computations, that's kind of the model that Reach gives for interacting with large categories of users. So we're going to do a parallel map reduce where the data that's being reduced is a mapping from users to a digest. And then we're also going to keep track of how many users there were. As this program runs, we're going to guarantee that the balance is always equal to however many tickets we've sold. So we're going to multiply how many by the ticket price. And then we're going to run this until the deadline hits. And then what will happen is that inside of this, every player who attaches is going to first confirm that they want to pay this ticket price. After they confirm that they want that ticket price, they're going to pick a random number, and then they're going to commit to that random number. Then they're going to publish their commitment and pay the ticket price. And we are going to remember what their commitment was. And then we're going to update how many there were. And this right here will run for a certain amount of time that is set by the sponsor. So the sponsor may say this raffle runs for a week. And so you can buy tickets during that week. Then what happens after? What happens after, I'm going to skip this, is that we're going to do another parallel reduce where now no one can buy any more tickets. Now what everyone needs to do is they need to reveal the secret that they computed before. So we're going to come back and we're going to do another map reduce. Here we're going to remember what the numbers each one of them were. This is basically what order they revealed their ticket in, because that determines whether like the person who reveals second, their winner number 2. You know what I mean? And so we'll continue verifying that the balance is how many, and we're going to run this until either everyone has returned their ticket or another deadline is passed. So you'll have 3 days to buy tickets, 3 days to reveal, and then the winner is announced. What each player does is they're going to declassify their ticket. They're going to check to make sure that they actually did it before. This is just kind of making sure that clients have basically run both blocks. Then they're going to publish their ticket. We're going to check to make sure that it's valid. And then what we're going to do is we're going to say, okay, you are now winner number 8. Or sorry, your ticket number 8. And then what we're going to do is we're going to compute who the winner is. The way that we compute who the winner is the sponsor publishes their secret information. We check that it's valid. Now what we can do is we can take all of the randomness from each one of the tickets, combine that with the randomness of the sponsor, and now we get a random winner. And then what we do is everybody knows what this random winner is. So then that one winner, what they do is they come back and they say, I am the winner. And we double check that they're the winner. And if they are, they get all of the money.
Got it. That's cool.
So notice.
Yeah,
go ahead.
Sorry. No, you.
Okay, so notice that this computation, it follows the same idea of normal reach programs where we say, okay, well, in the beginning, the sponsor does this. And then all the players do this for a little while. And then all the players do this other thing for a little while. And then the sponsor does this thing. And then one player comes back and does something else. And
But the
so
one player is forked off and everybody doesn't need to worry about that one player. He just eventually needs to get in here and do his withdraw. That's cool.
exactly. And the same sort of design paradigm that Reach provides, where you focus on what people do. You don't really think about what the state of the smart contract is. I mean, you kind of do that a little bit, right? Because you have to think about like, well, how do I know who the winner is? But the thing is that that's not really thinking about the state of your smart contract. That's just writing your program. I mean, that's just like doing the business logic. You're not stressing out about decisions like, what storage do I put this in? Or how exactly do I deal with how much memory is being used? All that is optimized and implemented behind the scenes by the Reach compiler. And you can focus on the high level idea about what it even means to do an auction. And of course, there are many ways to do an auction. This is just one way to do an auction. Like this whole idea where there's like these two phases, maybe you can come up with a way that's faster than that. There are all sorts of ideas that people can have when they write dApps. And kind of the goal of Reach is to make it so that there aren't 6,000 people who write dApps. We want there to be 10 million people who write dApps. Because right now, the only way that blockchain is going to really explode is if there are massively more numbers of users. And when I say users, I don't mean people with wallets walking around. I mean developers producing interesting programs. We had smartphones for a lot longer than there was the iPhone. But the thing that was really special about the iPhone was making it easy to make a program and making the app store so that everyone could make their program and then publish it. We kind of see Reach, the point of Reach, as making it so that there can be that explosion of creativity of the applications. And that explosion of creativity, that's what's going to really bring in the users.
It makes a lot of sense. So it seems like there's just kind of like a new way of thinking, a new paradigm here of when you want to write a decentralized app, instead of thinking of it in terms of execution and storage and Solidity, think of it in terms of actors and almost like a turn-based game and how those actors are going to be doing things within those turns. And eventually, if you write it all out in this certain way, then Reach is also going to like make it very, very safe and know that everything is going to work exactly like you want. And I see what you're saying as like, this is a lot easier for someone to drop in and start using, and then it kind of spits out to vanilla JavaScript. So from that, like you're thinking like there will be sort of this explosion of developers. If this is easy, they can basically get in here and kind of like write the rules of the game. And that's what you want a developer to be thinking about. You want them to be thinking about the app they're building, not all the BS of having to figure that stuff out. What about like the current composability? So if we say something like ERC 721s, like NFTs, how do they work here, and how does that kind of paradigm slide into this paradigm?
Yeah. So unfortunately, despite my smile, I'm actually not perfect. So there are a few things that Reach doesn't support yet. And one of the things that we don't support is we don't support interacting with a Reach program to a smart contract not written in Reach. And there's no real like large technical hurdle to do that. It's kind of, it's almost kind of easy to enable that. But what we want to do is we want to make sure that we don't enable that until we have the safety story completely figured out. And so that is future work that we'll be adding later. But there is in principle no reason why that will be hard to do. The main way that we'll think about doing that, by the way, is that essentially what we'll do is we'll define a category of participant where that participant represents another smart contract. And the same way to think about how you specify who the participant is, what interactions they can have, that's really the way to think about other smart contracts calling you and you calling other smart contracts. So we have a story that fits in, it's not implemented yet. However, I think that an ERC21 is a little bit more specific though, because I kind of answered the question, what if I want to call some arbitrary contract? But ERC21s, that's much more like this whole pay and transfer thing, because you're really not talking about, I mean, of course, what you're literally doing is you're calling functions from other contract, but what you feel like you're doing is, I just want to pay you not in Ethereum, I want to pay you in some other currency. So the way that will work is that basically what we'll do is, see right here where we say, where this wager is a uint, we're going to change it so instead it'll be something like an external token, or something like that. And the idea there is that now when you call that, you're going to say, well, Alice is going to say, I don't just want 10, I want 10 of what? And she's going to specify what that thing is. And then like ERC20, essentially what that means is that she'll specify like the address of the ERC20 smart contract that manages that particular currency. So again, the way that we're going to do this fits in with everything I've told you so far, but it unfortunately has not been implemented yet.
There is kind of like this double-edged sword of, once everybody comes in, there will be a bunch of composability, but you have to get everybody to come in to get to that composability. And in order to come in, and there kind of is this paradigm shift. You have to start over. You have to start with, you know, a new way of thinking of things, a new language. But again, you said like it does all compile to JavaScript eventually, and you do get to those other languages. It's interesting. I feel like you guys have some hurdles ahead of you about just basically like developer adoption and getting a developer to come in. When I think of what is the developer thinking, it's probably like, okay, I want to build a multi-sig app or something like that. How fast is it, you know, like if I use Reach, if I use something else, which one am I going to get done with at first? And right now, you might find more examples over on the other side, but it sounds like you guys are kind of slowly building this stack up, or quickly building. You're building this stack up to kind of have that for the developer once it gets there. It just seems like there is a body of work. There is ground to cover to get to be able to compete with the state of the art in terms of ease of use, even if this is like way more secure, the Austins of the world still want to get something out the door by Friday, right? So
Yeah.
There is going to be some trade-off there.
Yeah, what I would say is that like we are absolutely interested in being the easiest thing for developers to use, and we argue that we are. The thing though is that people that are already experts, who have already invested the time in learning the complicated interaction of Solidity and exactly how EVM works, I mean, they've already made that investment. You know what I mean? And it's understandable that they're used to their tools. But I think even for people like that, the main thing that we provide is we provide that security. So even if you walk into this with the model of, okay, well, I already know how to do this. All I want to do is convert my Solidity program to Reach. It turns out that actually that is totally possible to do. Essentially what you would do to take an arbitrary Solidity program and make it a Reach program is basically just to make a single giant parallel reduced construct that where the thing that you're looping over is whatever you already determined the state of your computation to be. And then just define a different participant for each different method and have each one of those do something. It's kind of like a, you're not really making use of the most interesting parts of Reach, but it totally works. And yeah, maybe I'm a little bit flip, but I kind of feel like you know, when there are 10 million developers of blockchain applications in the world, no one's really going to remember who the first 6,000 were.
That's true. That's true. Yeah. So I guess. Oh, go ahead, Chris.
I was kind of talk about adoption already. The thing that we kind of decided early on is that the current Solidity developers were welcome with open arms, saying we'd love all of you. But what we found is that just the regular developers are adopting us very quickly. I mean, we opened our doors beginning of September and said, hey, okay, here's our documentation, let's go. And just through word of mouth, the regular developers, we have now over 100 active developers on the platform, and this purely coming from the full stack developers. So like that's really where we're kind of making the big push, is the ones that haven't spent all of the time learning the tools.
What I'm interested in is like, what products are they building? Like, what are you seeing come out of this?
Yeah, so far the most prominent are the ones that started early, because everybody else that is just starting, they're building the products we told them to build. But
Right.
The ones that are actually really kind of like leaning into this are really seeing this as actually a great thing for gaming. Really building the assets that games will actually use. I don't know, it's because if it's rock paper scissors is our first tutorial or what have you, but that's kind of what we're seeing. And in the new future, I'm not allowed to actually say who yet, but we've actually contracted with one of the largest dexes on Ethereum to rewrite their platform in Reach. And part of that contract is to actually create a tutorial on how to actually build a secure, stable DEX So that right there is one of the very complicated things that you don't want to get wrong. And when we're able to show that you can write an entire DEX, both the actual client side and reach, in under 200 lines of code, I think that will really like
Yeah,
show the strength.
that'll bridge the gap for guys like me who have built similar things to see that written in this language and see that reach is capable of those things. That'll be really cool. That's awesome
Right.
to hear. So it is almost like your target audience is basically good developers that are just getting into blockchain development and are it's sort of like when I do the onboarding into Ethereum, there's a lot of gotchas and you have to talk through a lot of different, like, here's how you're going to have to track your big numbers and storage is expensive and here is why. You take them through a different mental model, but eventually building the same thing of there's sort of like these actors and here's how they interact. And it's funny because when I do my mentorship sessions, I always talk about like Ethereum is the greatest massive multiplayer RPG ever built. And you guys are really taking that to the next step here with like each of the actors, each of the players within the game. And we always, we deploy a contract in it, we send it value. And I talk about, oh, hey, now the contract itself is just a player in this game. You guys basically make the model after the player, basically like it starts with the player and how the players interact. And you focus on that as your paradigm of how do players interact, what do the turns look like, and it does like very much feel like a game in my shallow mental model of it from the last hour. But seeing something like a dex, that makes a lot of sense. But I guess there are just like players, right? There's reserves, right, that are stored in the contract, and then there are players that want to get in and put one asset and get another asset back. So I can start to apply the model, even though I've just kind of picked it up. But I'm sure there's a lot more there to it. But I'm
Yeah.
starting to get it.
And this
Yeah,
is
I think you understand it very well.
the way that I see it. This is just the beginning. We're building the reach language, but I definitely see like in the future, people building something like what you did with your scaffolding is, point and click, where rather than you're actually dropping like functionality, you're dropping participants and, drop in like, okay, this is what the participant would do. And it would automatically generate a reach application rather than a Solidity application as well.
Yeah, that's exactly my focus is trying to make that hackathon stack and get someone from zero to prototype as quick as possible. And I think that you guys will eventually be there. You guys are kind of working on some lower level stuff here though. Like this is different than I'm building React components, right? Like you'll get to that when everything else is there. But I would love to see that too. Like some more front end scaffolding where I can bring in components and kind of build a more feature rich app that is backed by a reach app.
Yeah,
Awesome,
we'd love
guys.
to say that too.
Yeah. Any closing remarks? This is neat. Thank you for. I feel like I got a great one-on-one demo, but hopefully I'll get this out on my YouTube and have some other people watching it too. But any closing statements on this?
My closing statement is even if you're an Ethereum developer, if you're an Ethereum developer watching this, give it a chance. Don't just read through the tutorial, actually type through the tutorial. Experience that wow of, of those security features that Jay pointed out of, what happens if, Alice doesn't get paid all of her money and things of that sort of stuff that you would normally get really burnt on if you didn't do it correctly. And I mean, not only is this, but there's actually other safety features that are built into the tutorial. Like we guarantee that both Alice and Bob have an equal chance of winning. That's we show you how to actually build and how to run through all of the potential scenarios. And it's really powerful. And the main thing is that Reach has 3 pillars that we stand on. And the funny thing is depending on the persona that you are, you will actually gravitate to a different persona. Like a new developer will gravitate to how easy and fast it is to actually build Reach applications. An existing Solidity developer will gravitate toward the security feature of it. And then in the future, when there are actually more chains that have more popularity, those type of developers will actually care which chain they launch on without having to change it. Because talking to full stack developers, one of the things that they really care about that haven't jumped in is what happens if Ethereum goes away? I mean, hopefully it never does, but what happens if XYZ chain goes away? Well, do I have to rewrite my application? Well, no, you just write your application and we launch it wherever. And that's the other great thing about this is that we say that we're blockchain agnostic, but truly we're protocol agnostic. This next month, we're working with off-chain labs to make it so that when you deploy, it doesn't actually deploy to Ethereum. It's going to deploy to a off-chain labs node. Because what happens if you write your application once and decide later, oh wait, I actually need some more scalability, you shouldn't have to change your code for it. So like that's really kind of our mentality around all these things.
Awesome. Thank you, guys. Yeah, and just to like lean into that a little bit, I noticed in the Solidity there was kind of like these bytes 32 that are tracking state or something like that. It felt almost like a roll up or something was going on there. Like you had some of the computation and state rolled up and you were only publishing hashes. Is that what's going on in the Solidity under there?
Yeah, this is the Merkleization that I mentioned before.
Okay.
So one of the things that we try to do is we try to optimize your storage so that basically you can kind of, here's a really simple way to think about it. Imagine if you were writing a program and you had 3 variables, but at any given time, you only ever use 2 of those variables. Then what you could do is you could actually make it so that your program really only has 2 variables and you just switch the meaning of them. Now that would be something that would be a terrible idea to do by hand because you would do it wrong. Okay, but we are a compiler, and so we can do that analysis one time and get it right and prove that it's right. So then we can actually optimize your storage. We basically do something like that to guarantee that your storage is minimized over the course of the execution of your program.
Neat. That makes a lot of sense. Yeah, it's cool thinking about the 3 pillars and how different people lean into them, and how you guys are thinking about it underneath, and how the abstraction is about creating the program, but underneath you guys are setting up a lot of safety guarantees and focusing on making sure that the thing, there's no way for the thing to break. So great job, guys. This is really cool. Thank you for demoing it today.
I really appreciate you taking the time.
Oh yeah, awesome. I look forward to see how this progresses, right? This is kind of like laying the pavement and seeing who drives on it and how it works out.
Yeah.
Awesome. Guys. Thank you.